I would like to present a recently funded project to initiate a mine water geothermal system underneath Durham University. So, like many towns in the northeast of England, Durham has a significant mining history, coal mining history, and actually a number of the coal seams are located right underneath the Science campus of Durham University. So the map here shows the south side of Durham. So in the north we have the central peninsula, the Durham Peninsula, and the area we're looking at here is in the center has the Science campus. And the colors here on this map are two mined coal seams. The shallow one, the Hutton seam, is only 62 meters deep. It's not very voluminous, and so relatively speaking, it didn't extract a lot of coal. But the deeper one, the Busty seam, extracted a lot more coal, and therefore now contains a lot of mine water. It's also deeper, 145 meters, so the water temperatures and the rock temperatures there are a bit higher. Durham also has plans to build a heat network on its campus. And if that is going to be materialized, that would be an ideal opportunity to also look into the possibility for a mine water heating system. And in addition, there is also a data center on the campus that has a high performance computing system that at the moment has a capacity of, it produces waste heat of just under a megawatt. But the university is planning to expand that to 5 or maybe up to 10 megawatts. And then we have the two coal seams I just described in the previous slide. So these three ingredients actually make it quite a suitable location, perhaps, for installing a mine water heat system. So when funding opportunity came around, we decided to apply for this. And this got funded, and basically what we are going to do in the project, we said we were going to do in the project, is to install an immersion cooling system on the high-performance computing center. So essentially, the computers that are installed there, or part of them, are going to use a new cooling technique, which is completely submerging the computers into a liquid that extracts the heat from it, and then the liquid can be transported to do something else with it. We plan to drill into the mine workings, both the mine workings underneath the campus. And then with that, we hope to test the possibility for using these mine systems for heat extraction and perhaps heat storage. And the emphasis here is on testing. So it's not meant to just be a project that provides a low carbon heat for the university, although of course, the university is very much hoping that it will, but it's really meant as a research facility and also an opportunity for educational purposes because several departments are interested in providing educational materials. And in addition, then we hope to do some feasibility studies in terms of modeling. Now, this project only recently got funded, and we're still in the stage of negotiating with the university what's possible, applying for licenses and so on. So, unfortunately, I don't have actually many results to show you yet about the project, but one thing we have been doing is some modeling to do some preliminary study on the feasibility of the mine workings underneath the campus. Now, most of the modeling tools that have been used in the past to look at whether mine water systems are feasible or not, they're actually kind of in two categories. One is using simple analytical techniques to explore these. And these techniques are fast, but they struggle to deal with the complex geometries of the mine systems that we know, that we've been seeing. On the other hand, we have models that are fully 3D and can deal with the full complexity of the models, and can also deal with the complex geology that surrounds the mine workings. And we saw these galleries project presentation earlier today that nicely illustrates what's possible with that. Now, these 3D models, unfortunately, can sometimes be quite computationally expensive. So what we were aiming for in terms of modeling was to do something in between. And we developed a tool that is relatively fast because it uses semi-analytical solutions. And we also divide the mine plans into simple, discrete units that actually speed up the calculation. So we developed a tool that is fast enough so you can do lots of parameter studies, lots of different calculations in a relatively short amount of time. You can do this on a laptop as well. But of course, you can't expect all the details and the precision of the full three-dimensional models that we saw earlier. The way the modeling is set up is that we have to go back to actually the mining procedure. So hole mining was done with basically two methods, as probably most of you are aware of. There's on the one hand, we have the room and pillar mining, where the photograph on the left shows that this creates tunnels or galleries, and we modeled these using a pipe network. The other technique was longer mining, where the entire core layer was extracted. That leads to the collapse of the core layer, and we modeled that with a porous medium. So the modeling tool then consists of 3 steps. First, we digitize the mine plans into discrete units. And then for each of those units, we calculate how the water would flow through those units. And then connect all those units together, and then we know how the water would flow through the entire system. Once we know how the water is flowing, then we can calculate, again, for each of those units, how much heat exchange is going to be between the water flowing through the mines and the rock surrounding the mines. And from that, we can calculate the total heat exchange. So here's a calculation that applies this technique to the mine system underneath the Durham University campus. So what we're looking at here is a 3-dimensional view of the 2 coal seams, the 2 mined coal seams. Water is abstracted from the bottom seam, that's the red triangle, and then re-injected into the top seam. The bottom seam has a rock temperature of about 13.5 degrees, so the water we pump up has that same temperature. We assume that a heat pump will then take out approximately 5 degrees, so we re-inject the water in this model with 8.5 degrees. That 8.5 degree water is then flowing through the Hutton seam, the top seam, to the north. So we're looking north here in this picture, and then it flows. It goes around to the shaft you see in the middle of the plat, flows down into the bottom seam, and then back to the abstraction point. And ideally, during that journey, the water then warms up again to 13.5 degrees. But as you can see in this calculation, it doesn't really. The actual temperature for this particular scenario, which is 64 liters a second pumping rate and a duration of 30 years, you end up with water temperatures, according to this model calculation, about 10.3 degrees. So clearly less than the 13.5 that is theoretically possible. So what you can conclude from this is that perhaps for this particular setup, the mine system is not feasible of sustaining long-term heat extraction. Is there a way around it? Well, one simple way would be to reduce the pumping rate. Okay, so if we go from 64 to 6.4 liters a second, so only 10%, that helps. That would then lead to abstraction temperature of 12.7, so that's pretty close to the theoretical maximum. But of course, that reduces the capacity as well. And then you wonder if it's worth the capital investment of drilling into the mine workings if you only get a little bit of heat out of it. So another approach is to actually use the waste heat that's available from the data center. So this is some modeling I recently did. This is not yet part of the software, the GEMS Toolbox software that we have developed. I only recently added it to it. But it illustrates what's possible So essentially what you can look at is seasonal variation, and we've been discussing this over the last 2 days. So in the winter, you still extract the heat, but then in the summer, you re-inject the heat from the data center. And then you get this oscillating injection temperatures you see in the bottom left. That leads to an oscillating output temperature as well then, and that's on the plot on the right-hand side, and you see that the output temperatures then start to fluctuate between something like 11.5 and 13 degrees Celsius. So if that is acceptable, then this is perhaps a possible solution. So as was said before, essentially if you balance the heat extraction with heat injection, then you have a system that is basically suitable on the very long term. And as was mentioned earlier as well, this is the system that Heerlen has been using for a while now. So to conclude, we plan to set up a mine water geothermal system underneath Durham University. We don't have any results yet, but preliminary modeling suggests that the system itself is not really suitable for constant heat extraction, but we need to re-inject heat to make it more feasible. And then finally, I'd like to say that there's a lot of things that we are still dealing with. We just started the project. There's a lot more questions than answers at the moment. One of them are listed here is the effect of local groundwater. This is clearly something we need to look into, but at the moment we don't have any data available about local groundwater flow. We're also looking at the optimal site to extract and re-inject the water, and that includes maybe also looking at alternative sites to like Akeley Heads in a different part of Durham, where to apply this technique. So again, more questions than answers, but as several people today earlier said, it's time to actually start building a project that does the work rather than just talking about it. So that's what we're planning to do here. Thank you very much.